Alright guys, so today we're in section 11.4 looking at partial fractions. And so when we have two fractions that we're trying to add together, what do we need to do? Well, we need to find common denominators, right? So for our example here, 2 over x plus 1 plus 3 over x plus 2, the LCD would be x plus 1 times x plus 2. The left hand rational is missing x plus 2, so we multiply it to the bottom and to the top. Then we distribute. We do the same thing to the right hand side, except this one is missing x plus 1. Okay. We sum the numerators together. We get 5x plus 7 over x plus 2 times x plus 1. And then we distribute the denominator to get 5x plus 7 over x squared plus 3x plus 2. Okay, so that's something that we've done plenty of times this semester before. But how do we work backwards? If we were given 5x plus 7, how do we get back to the two fractions, those two partial fractions that we started with? Okay, and so if we look at 5x plus 7, since we already know the answer, we're ending up with an a over x plus 1 and a b over x plus 2, where in our case 2 is a and b is 3. But why would we just assume that it's just a and just b, right? And not like 3x plus 2 and 5x plus 1 or something like that. And so, well, the reason comes from something that we've covered already actually this semester, which is long division. And so if you were to, for instance, have an ax plus b where, for instance, let's say 5, let me write that better here. So let's say ax plus b was like 5x plus 1 or something like that. And this was 2x plus 2. That's just replacing these guys just for an example. Why is that not possible? Well, if we divide x plus 1 into whatever the numerator is, because x plus 1 and ax have the same power, that means x can go into ax plus b, right? When we did polynomial long division. And so if we look at the example here on the left, you'll see that if we divided x plus 1 into 1/2 x plus 2, it goes in 1/2 times. We multiply 1/2 to x, 1/2 to 1. We subtract, and we get 3/2. And so our remainder becomes 3/2 over x plus 1. But what you'll notice is with the fraction that we started with, we don't have a number like out here being added to our fraction, right? We just have the fraction, and that's all we have. So if you just have the fraction and you do this long division, well, you'll end up with a number plus whatever the remainder is over x plus 1. And likewise for the second fraction, you'll end up with a number plus whatever its remainder is over x plus 2. But because our original rational doesn't have a number outside, right, out in front, it's a proper fraction where the degree of the top is only 1 and the degree of bottom is 2. And because that's the case, it must be that these two numbers, like the whole divisible parts in front of our rational parts, they must have added to 0 and gone away. And so essentially what that's telling you is that you can try to, you could assume that you do have an ax plus b and a cx plus d rather than just a number on top. But what that will do is that you'll just end up having a whole number as opposed to even ending up with a fraction. So you have a whole number plus a fraction and then another whole number plus a fraction. But because the rational that we started with doesn't even have any whole numbers in front of it, that must mean that those two whole numbers added up to 0, like they disappeared. So this is kind of going to drive our discussion about what are the possibilities when we're trying to break up these fractions. What are the possibilities for the numerators? And using what we know about long division, the remainder on the top of a fraction is always going to have degree less than the denominator of the fraction, right? So when we do long division, sure, we might get some sort of polynomial or value out here, but the remainder is always going to be something where the degree of the top, right, the amount of x's on top is always less than the power of the x's on bottom. Okay, and so this is going to drive our decision making on what is possible for the numerator when we do partial fractions. So the first rule is that you should always make sure your fraction that you're starting with is proper. And what we mean by that is that the degree of the polynomial on top must be less than the degree of the polynomial on bottom. So this is saying to the right here, the degree of f of x must be less than the degree of g of x. If it's not less, then what you need to do is actually you need to do long division before you start trying to break up any of these fractions, okay? Now, this won't be super important. I don't think any problems in the homework are going to give you improper fractions, but it's something you should be aware of because you will see this topic pop back up in Calc 2. So the first rule, make sure your fraction is always proper. So we don't want to see anything like this, where the degree of the top one is bigger than the bottom. If this happens, what you want to do is you want to divide. You want to do long division, and so you make sure that you end up with something where you want to make sure you end up with something where you have only a fraction, right? We don't want this kind of stuff out in front. So make sure that the fraction is always proper, okay? And so, for instance, let's say we did have this, what would we need to do? Well, we'd want to do long division. How many times does x go into x squared? It goes in x times. X times x is x squared. X times 1 is x. Okay, so what we should have done here is given us a little space. And so now we subtract this, and so x squared minus x squared is nothing. 0 minus x is negative x. We bring down the 1. And how many times does x go into negative x? Well, it goes in negative 1 times. We get negative x minus 1. We subtract. So we get 1 plus 1, which is 2. And so this becomes x plus 1 over 2 plus x plus 1. And so you would want to change this into this. So x squared plus 1 over x plus 1, you would rewrite as x minus 1 over 2 over x plus 1. And then you can see here, there is no decomposition to do. This is the only part of our fraction. There's no possible way you could break this up. But like I said, this really won't be happening for us. This is more something that you'll need to be aware of when you do partial fractions in Calc 2. So after you notice that the fraction is proper, i.e. the degree of the top is less than the degree of the bottom, you should only start your decomposition after you factor. So what do we mean by that? Well, if we look at this problem here, the one we originally started with, we went the opposite way. But if we wanted to decompose this into whatever two parts it is, we have to make sure we factor everything that we possibly can. And so 5x plus 7, there's no LCD here because 5 and 7 are relatively prime, so that the numerator is going to stay the same. But in the denominator, if we think about using all the tools that we've learned up to this point in the semester, we'll notice that we're looking for numbers that multiply to 2 and add to 3. And so that is positive 2 and positive 1. Because the x squared has just a 1 in front of it, we know that this factors into x plus 2 times x plus 1. And so we don't want to start our decomposition looking at this. We want to make sure that we factor any of the polynomials on bottom that we can before trying to decompose into our partial fraction. Okay, so that's rule 2. We just took care of rule 2. We took care of rule 1 because the degree of the top is a power of 1, the degree of the bottom is power of 2, and so it checks out. It is a proper fraction, so rule 1 checks out. Should have done that earlier. Rule 3 says when decomposing the fraction, your arbitrary numerator must be exactly one less than the denominator. So now what we're doing is we're looking at our unique terms on the denominator, and we see that our unique terms are x plus 2 and x plus 1. And since these are only a power of 1, the only polynomial that has degree less than 1 is a degree 0 polynomial, which just basically means how are you going to have something with a degree less than 1? Well, you must have a degree of 0, which means it has to just be a number. You can't have any x's up here. So we just put an a up here. That's just a placeholder for any number, any possible number. And the same for this one, right? It has degree 1, and so the only possible polynomial we could put up there we would have degree less is just a number b. Okay, and then rule 4, so we just took care of rule 3. Rule 4, repeated factors must be accounted for. And so here we have x plus 2 and x plus 1. We don't have any repeated factors. These are both unique factors, so we don't really have to worry about rule 4, but we have some example problems that we'll set up together where we do have that. So let's just check that off for now. And so this becomes the setup for our partial fraction decomposition. So now that we have our setup, how do we figure out what a and b are supposed to be? Well, you take the factored part, and so you say 5x plus 7 over x plus 2 times x plus 1, and you set it equal to your partial fractions, a over x plus 2 plus b over x plus 1. And now what you're going to do is you're going to multiply both sides by the LCD. So it's going to be x plus 2 times x plus 1. You multiply it to the left. If you do it to the left, you must do it to the right. Notice that these terms are going to cancel with the denominator of the thing on the left. So on the left-hand side, we're just going to end up with 5x plus 7. And then on the right-hand side, what we're going to have is x plus 2 and x plus 1 times a over x plus 2. When we FOIL it here, when we FOIL these two terms here, the x plus 2's will cancel. And so we'll just get a times x plus 1. Okay. A times x plus 1. And then when we FOIL it to this term, well, this time the x plus 1's will cancel, and we're just going to get b times x plus 2. And so we can FOIL this out, and we'll get 5x plus 7 is equal to ax plus a plus bx plus 2b. Okay. So now what we have is we have a 5x, an ax, and a bx, and all of these terms have x's, so what we can do is we can make a new equation with them. And so we'll say we have 5x is equal to ax plus bx. All right, and then our second equation, well, we have number 7, just the letter a, and just the letter 2b with no x's in front of it. So we can make a second equation with those guys. So we'll have 7 is equal to a plus 2b. Okay, well, here we see that both of these terms have x's, and so does the 5. You can factor the x out. You'll get a plus b times x equals 5 times x. And so this is another way of telling us that a plus b must equal 5. Okay, and we have a plus 2b is equal to 7 from this equation. If we subtract a from both sides here, we'll get b is equal to 5 minus a. And what we can do with this is we can take this equation and replace the b in this equation with 5 minus a, because b is equal to 5 minus a. So we get a plus 2, 5 minus a is equal to 7. We get a plus 10 minus 2a is equal to 7. Combine like terms, we have negative a plus 10 is equal to 7. we subtract 10 from both sides. We get negative a is equal to negative 3. We get a is equal to 3. Okay? So we have a is equal to 3. And then we can come over here and we have b is equal to 5a, but a is 3, so 5 minus 3, and that tells us b is equal to 2. And so if we scroll up, we have b is equal to 2 and a is equal to 3. That tells us that the original composition was a was equal to 3 and b was equal to 2. And so if we keep this in mind and scroll all the way up in the beginning where we started our lecture, look, it's 2 over x plus 1 and 3 over x plus 2. That's exactly what we ended up with. So we ended up getting the same composition that we started with. So partial fractions are the way of going backwards from having common denominators and combining two fractions. Okay? So now let's get a little more complicated with the possibilities that we might have. So we're just going to practice the setup here. Now, we have our 4 rules, so I'll go back up and grab those so that we make sure that we follow them. Okay, so here are our 4 rules. We want to make sure our fractions are always proper. We want to only decompose after we factor. We want to when we decompose the fraction, we want to make sure our arbitrary numerators must be exactly 1 degree less than the denominator. And then we want to make sure that repeated factors are accounted for. So we're not really super interested in the numerator here at the top, but the only thing we do want to make sure is that our fraction is proper. So is our fraction proper? Well, the fraction has a degree 1, the numerator, but the denominator has x squared and then another x. So in total, this would be x cubed. And so x to the first is definitely less than x cubed, so it is a proper fraction, so that checks out. Okay, so we only want to decompose after factoring. Well, luckily for us, this one is already in its factored form. X plus 1 squared times x plus 2. There's nothing else that we could do. They're all linear. Okay. When decomposing the fraction, your arbitrary numerator must be exactly 1 degree less than the denominator. So our unique denominators are x plus 2 and x plus 1. Okay, right? We have x plus 2 and x plus 1. And so, well, since this is a degree 1, well, our numerator just has to be a number. Since this is a degree 1, our numerator just has to be a number. Cool. Okay, rule 4, repeated factors must be accounted for. And so what that's telling us now is that, look, that we don't just have x plus 1, but we have x plus 1 squared. So we do have it to the first power, but since it's a repeated factor, now we need to take account for it. So we need to also have another partial fraction where we have not only the first power but the second power. But because the inside term is still only linear, all we have to have here is just a number as well. Okay, so no matter how many powers this x plus 1 have, the inside term is only linear, so we're only ever going to have something larger than the linear power. Okay, so that's the setup for this specific one. All right, let's go down to the next one. So is the fraction proper? Well, the degree of the top is 1, the degree of the bottom is 3 and 2, so 5, so yes, it's proper. The next thing we want to make sure is everything factored as much as it can be? Well, yeah, we have x cubed, which is just x times x times x, and x squared plus 1, well, what we could notice this is the sum of squares, right? X squared is a square, x times x, 1 is a square, 1 times 1. Since it's the sum of squares, we know those don't factor over the reals, so it is already in its factored form. Okay, and so now we're going to take a look at our possibilities, and so we have a, over, we have x, right? So that's one of our powers. And then we have to remember that we have to account for repeated factors. So we have x cubed, so we should have a to the x over x. Then we need b over x squared, right? Because inside the parentheses, it's only a linear term, plus c over x cubed. And so now we've accounted for all of the powers of the x term. And then our fourth term is x squared plus 1, okay? But the rule 3 says our arbitrary numerator must be exactly 1 degree less than the denominator. And so since our denominator has a power of 2, right? That means our numerator must have 1 degree less than that. So instead of being just a number like a, b, and c, it must actually have an x in it because it can only be 1 degree less than the x squared. And so there's our setup for the second partial fraction. Okay. Now for the next one, so we'll look over here. We have an x plus 1 squared. Well, because x plus 1 is linear, we know we have a over x plus 1. Because repeated factors must be accounted for, we have another b over the second power of x plus 1. Then we have our next term, x squared plus 1 squared, right? And so since this can't be factored, we talked about why it couldn't be factored in the previous problem. The numerator, the arbitrary numerator, must be only 1 degree less than it. So since it's x squared plus 1, that tells us that our numerator must be cx plus d, right? Over x squared plus 1. And then because we have it to the second power, we have to account for that and create another one of these, x plus 1 squared. And we just have to create, it's still, inside the parentheses, it's still a power of 2, which means our numerator must be a power of 1 because it can only be 1 less than it. And because we have to account for all of the powers, we have to create a new fraction with possibly different coefficients. Okay, and so let's look at this guy. So the first thing we got to make sure is it a proper fraction? Well, the degree of the top is 1, the degree of the bottom is 2, so it is proper. The second thing we want to do is want to make sure it's factored. So is it factored? And so if you were to say yes, if you think this is factored, then what our decomposition would look like would be just our numerator has to be 1 less than it, right? So ax plus b over, and then the denominator, which is x squared plus 10x plus 25. And so what you'll notice is this doesn't really help you at all because it's basically telling you that a is 3 and b is 7, and it can't be broken up any more than that. But that's because we didn't notice that the bottom is actually not factored yet. So if you take a look at this again and you see x squared plus 10x plus 25, you're looking for two numbers that multiply to 25 and add to 10. And so the factored form of this would be x plus 5 times x plus 5. And we would want to rewrite that as 3x plus 7 over x plus 5 squared. Okay? And so our decomposition, our partial fraction, is going to be, well, x plus 5 is linear, so it only needs a power, or it's only linear, so it just needs a constant on top. And then because we have to account for repeated powers, well, we're going to have another one with the squared term. Okay, so let's go ahead and complete this one and figure out what a and b are supposed to be. Just to show another example, so we have 3x plus 7 over x plus 5 squared is equal to a over x plus 5 plus b over x plus 5 squared. We're going to multiply both sides by the LCD, which is just x plus 5 squared. This is the numerator and the denominator will cancel, leaving us with 3x plus 7. This will always happen. Here we have to distribute. Well, the first x plus 5 will cancel with the denominator. The second one will multiply to a, and we'll get ax plus 5a. So let me slow down here. A times x plus 5. Here, though, since these also have the same denominator, this is just going to cancel, and we're just going to get b. And so what we have is 3x plus 7. And then we can distribute this a to these two terms, ax plus 5a plus b. So now we have two equations. We have ax is equal to 3x, and we have 5a plus b is equal to 7. Well, this tells us a is equal to 3, right? Straight off the bat. Well, if a is equal to 3, that means we're going to replace this a with 3. So 5 times 3 plus b is equal to 7. That's 15 plus b is equal to 7. We subtract 15 from both sides. That tells us b is equal to negative 8. So our partial fraction decomposition for 3x plus 7 over x squared plus 10x plus 25 is equal to a being 3. So we get 3 over x plus 5. And then b is negative 8. So we get plus negative 8 over x plus 5 squared. And that is our partial fraction for this original question. Okay, so I will also link someone else's explanation on partial fractions just in case you don't like mine, because it can be a confusing topic to try and wrap your head around. But if you do have questions, you can see me in office hours or send me a message. I'll be sure to respond as soon as possible. All right, well, I'll see you in the next one.